very good morning, good afternoon and good evening to all the participants, students and who are taking this course under NPTEL MOOC. The title of this course is Application of Forecasting, Regression and Time Series Analysis, and my good name is Raghunandan Sengupta from the IME department at IIT Kanpur. So, as you know, the three main topics are forecasting, second one is regression and third one is time series, and we are covering the last part, which is time series analysis. This is week number 11 and lecture number 54. So, as we continue in the introduction and the examples is basically the coverage we will try to cover in maximum of the lectures for time series, without going to much of details of proofs. Now, what are the conditions of stationarity? So, if you remember, we have discussed that in stationarity the main two criteria are the first moment, which is the mean, and obviously the main issue is about the concept of variance, which has to be controlled, because if variance is dependent on time, then the problem of trying to predict becomes difficult. So, conditions of stationarity of a moving average process and its related information will be discussed here. A linear process represented as a moving average is stationary if its statistical probabilities do not change over time. Thus, for a moving average process, a constant mean would imply that the expected value of the process is constant. That means, you want to find out that even if there are variability, the expected value continues to be fixed. For the moving average process with white noise error. So, if you remember, white noise is the external factors which are affecting, which we will call as error in regression models, called error in forecasting. We are using the concept same here as white noise. So, the white noise errors are, in the simplest sense, would be with constant mean, which is 0, and if you remember, we have also mentioned that the variance is sigma square without any suffix. Suffix means it is there is a suffix, means it is dependent on time. A constant variance, if we come to the concept of stationarity, would imply that the variance of the process must also be constant and finite. So, you will basically have two concepts: constant mean first moment, constant variance second moment. So, let me continue reading it. Constant variance implies that the variance of the process must be constant and finite. Thus, for a standard moving average process, the variance is a function of the white noise, which is basically external coming with a variability of sigma square, and the square of the weights depending on the effect of the white noise as time progresses. So, which should remain constant if the sum of the squared weights are infinite, in the sense that if you have the weights as given, I will just highlight it. So, if the weights are given by sigma this phi j, and j is basically being the indexing. So, I am considering the indexing from minus infinity to plus infinity, considering whole range of the weights, but obviously, if you are going to predict or forecast for the time series for the future time period, j would be indexed accordingly, because j index I am taking from minus infinity to plus infinity means the past, the present and the future, but in the later part we will see the j indexing will change, because we are trying to predict for the past, taking the present values accordingly, and even if the future values are taken, they would be indexed such that we will start the indexing from j is equal to 0. For a constant, and this is what I mean, for a constant variance, if the for the condition of stationarity as you are considering. So, x t is the time series. So, t suffix changing. So, if it is separate, in the sense that I will highlight, if the factor of sigma square and this sigma square, if you remember, is the variance of the noise which you have already defined properly, and if the weightages which you are giving in the square of that summed over from j is equal to 0 to infinity, depending on how many such predictions you want to do, also depending on the lags. If this is equal to the variance and it is less than infinity, then obviously it is a constant variances and it is not changing even with respect to j changing from 0 to infinity. Now, the covariances would depend on the lag, and we know that we are defining the lag by h. Thus, autocovariance we have already considered the autocorrelation function, autocovariance functions, and we have shown that in the graph. And if you remember, I had mentioned that we are only going to discuss the output without going to the detailed coding part. So, it will depend on the lag covariance. Thus, autocovariance between observations at different times must depend only on the time lag, not from where you are starting. So, if you are starting at t is equal to 3 and with a lag of 4. So, the dependence on the autocovariance function is only based on the value of h lag, not from where you are starting. So, obviously, for a constant covariance, now we have discussed constant mean value, we have discussed constant variance. Now, we are coming to the concept of constant variance. So, constant variance would mean that you multiply the white noises sigma square, which is the variance, multiplied by. So, now what we had for the variance concept, you have that small phi j square, but now with a lag of h, it will be small phi j into small phi j plus h, depending on the lags you are doing. So, the phi j's would basically be the weights with the corresponding suffix j or j plus h, whatever it is, it will denote at what time period you are, and h again I am repeating is the lag. Now, autoregressive integrated moving average, which we would be the main focus further on and the discussion, because based on that we will try to finalize how the time series looks like and what are the properties. So, the ARIMA process has 3 parameters. One is p, which is autoregressive coefficient, one is the integration parameter given by d, and another is the moving average, which is given by q. So, you basically have p, d, q, which we need to find out in order to specify what is the ARIMA process and what are the properties. Now, without immediately going into the model, first I will give you the results of 3 different time series which are mentioned in the Excel sheet. So, let me open the Excel sheet. So, the Excel sheet which you have, which you will get, as I had mentioned in all the subsequent previous classes, that you have been shared with the detailed Excel sheet for forecasting. You have been already been given the detailed Excel sheet for regression, and you will be also given the detailed Excel sheet for the time series. Now, if you see the time series, we have the time series again I am mentioning Indian rupees to US dollars rate starting from 2nd January 1973 and it goes on to almost 2024. The second one is UK population, and all the URLs are given for your kind information. Is given for yearly population from 1938, it goes to 2023. Then you have the time series of international airline passengers from January 1949 to December 1960. Then you have the Australian monthly electricity production given from January 1977 to December 1994, and you also have the other one data is basically passengers arrival, departure and transit at Frankfurt Airport starting from January 2015 to December 2024, and other data which we have is the sunspots on an average, and on the URLs are also given, and yearly average of sunspots, because month wise they change. So, we have taken the average and the URL is given. We have taken means I have taken the corresponding data, and as I again repeating, the URLs are given. This is basically from 1700 to 2024, and the other data point is we will keep adding as we progress. We have the NSE data for Bajaj, closing prices are given from, let me change, closing prices are given in Indian rupees from starting from 2nd January 2012 till 7 December 2012. So, this is almost a 1 year data. Obviously, it does not mean 365 number of data, it will depend on the number of days the trading was there, considering there are holidays on Saturday, Sunday and national holidays. Now, these are at present for the 54th lecture, these are the data. So, I keep adding the data depending on how the results are and how interesting the data sets are, because there are quite interesting data sets and they are actually which can be utilized. So, if I go back to the ARIMA PDQ, the slide where we have mentioned, again I am mentioning the parameter P is the autoregressive coefficient, integration parameter is D, moving average parameter is Q, and we take the UK population. First, I will draw the graph. This is the UK population, I take the year and the population, I am drawing the just the time series. So, if I draw the time series, this is the data which you have. So, I will not be saving the time series data, this is just for the illustration, the actual data sets would be there, you can do many things with the actual data set. So, this is the population change in UK from 1838 to 2022. So, it is given. Now, when I plot it and use simple ARMA model PDQ, the values are coming as this, the constant value, the ARMA 1, MA 1, and the values which come is basically the p value, which is the autoregressive parameter p is 1. Here you can see, I will just also try to highlight accordingly, just wait. So, this is the ARMA process with 101 and the values are given corresponding to the standard errors are given, because this is we consider the time series based on a sample and the standard deviation, the t statistics and the p values are given, which would basically be more related to how the estimation has been done. Because I am not going to go into the much of the estimation problem, because that will take us more into depth about the concepts of theoretical areas in the time series analysis. I will try to avoid that. Now, if I go into the other one is, if I go for the international passengers. So, where it is, this data set I will remove, international passengers is this one. So, there are 145 data, I will basically plot it. So, I will use the line diagram. So, this is how the international number of passengers travelling from January 1949 to September 1960. If you can add the data starting from 1960 to about 2020, you will get a huge set of data. The URL is given, you can check the net and add the data. So, this is how it will look like. So, there is a trend. So, I will just plot, this is the trend, and obviously, there is fluctuation. So, somebody looking from the point of view of forecasting also can comment accordingly, but I am only concentrating on the time series. Obviously, the question may come that the concept of time series and forecasting are related. Regression is not that much related like as the relationship is there with forecasting and time series. So, regression would basically be a little bit different from the concept of time series and forecasting. Yes, this can be also utilized for forecasting problem. So, this is how the data set looks like for international travels. So, if I go to the PPT slide, the while it is again an ARIMA process with 101 and the values are given and along with the standard deviation and the t statistic and the p values. If I go to the third value, Australian electricity production, again I plot it. So, I go to the time series. So, here it looks like how the time series looks like. So, again there is a trend, almost a constant steady increase, and there is a very nice seasonality concept of depending on, obviously you can guess depending on the load, which may definitely will increase during the summer, load may decrease during the winter, considering that load you think would definitely be much on the higher side in the summers, and obviously the population increasing and so on and so forth. So, the data set is from 1977 January till December 1994. So, the huge set of data which you have. So, if I delete the data, the plot of the data, I am not deleting the data as such. So, if I see for the Australian one also, it is an ARIMA 101 process with the corresponding values and the standard deviation. Now, this was just an illustration. Now, actually the ARIMA PDQ process would consider this model as such, and what are the terms here? If you see, you have the mean value, which mean value is basically the trend or the average value you are saying, and there would be two components. So, here the moving average parameters thetas are defined, so that their signs are considered as negative following the convention, but obviously depending on how you formulate the model, you can take it the positive or the negative part. Now, these sets of small phi and theta are corresponding to so called the weightages you are giving to two sets of terms. Now, if you see here, the suffix is important. So, if you see the first part, I will use the orange color. So, it is basically the multiplication of phi multiplied by the corresponding time series data, and if you see the time series data is considered till t minus p, considering the parameter for the ARIMA process. If you remember, p, d and q were there, and the moving average concept was based on the part that you will consider the average with the parameter of p. Now, when I come to the concept of the error part, which is the second set of values which you have, which I will use a different color, say for example, green. So, the weightages are theta 1 to theta q, suffix q, and if you remember, for the ARIMA process we have defined q as the parameter corresponding to the values as here. I will just highlight. So, you had values of p for the autoregressive concept, d being the integration and q being the moving average. So, if we have d here, then the theta concept would be correspondingly taken. So, if you consider here, you have phi 1 till phi p, remember, and in the other case you have theta 1 till theta q, p q d had been defined. So, often the parameters are defined such that they are known as AR1, AR2 corresponding to the concept of the part related to the moving average and the ARIMA process, and the moving averages part are considered as MA1, MA2 till MAQ. Now, what are the different equations which you have in the simplest form? when you have the concept of d as 0. So, d if you remember was the third parameter which you have defined. So, if d is 0, then obviously it means the estimated value and the actual value are equal. If d is 1, there is 1 lag. So, obviously it would mean x small x t. Remember there is a small x x and the capital X. Small x t would be x t and t minus 1, that is 1 time difference. When d is 2, there is 2 time difference. If you take the differences twice, then the equation basically comes out to be x t in minus 2 into x t minus 1 plus x t minus 2, because the minus minus of x t minus 2 would basically make it plus. So, you are taking the twice difference and adding them up accordingly. Now, what are the results for the PDQ model? And I will just give the results, come back later on as we progress. For ARIMA 100, this is a first order autoregressive model. So, if you basically understand that, trying to check with the results which we discussed would be much easier. ARIMA 010 is a random walk process coming from the concept of stochastic process. The ARIMA 110 is basically differentiated first order autoregressive model, depending on the order you are taking for the first difference is 1. ARIMA 011 is without the constant, means simple exponential smoothing, and we have already done the concept of exponential smoothing in forecasting. Now, exponential smoothing concept, to illustrate, we have done both the one parameter and the multi parameter, and if you remember the parameters which I take was basically alpha 1, alpha 2 and corresponding to what time period you are basically trying to find out the give the weightages and do the exponential smoothing concept. Now, if an ARIMA with 0, 1, 1 with a constant is there, it means a simple exponential moving average with there is a growth, and where would that growth come? If you remember again, in the exponential smoothing concept, we can take both as a parameter constant with respect to time and another parameter changing with respect to time. That is, the parameters are one was non adjusted and one was adjusted depending on the time frame. So, obviously, the constant term would imply that the parameters are adjusting depending on how you predict. If you have ARIMA 0 to 1 and or 0 to 2 without the constant, is a linear exponential smoothing concept, and ARIMA 1 1 2 without the constant would mean a damped trend linear exponential smoothing concept. Now, depending on the idea where p is equal to 0, 1, 2, similarly for d and q, you can almost plot all different type of time series analysis. Now, the reason I am saying that with the values of p, d and q maximum to the case of 2, all of the time series can be modeled, because depending on if for the to bring stationarity in the concept, with either the first difference or the second difference, you are able to basically make a non-stationary series as a stationary with the characteristics such that you can do some useful analysis for the time series as required. Now, the time series for the autoregressive 1 process, if it is stationary, then it will satisfy the concept as this. So, you will basically have the part with stationarity, means you would basically have an error term corresponding to the white noise, and the white noise has, if you remember, the white noise has a mean value of 0 and a variance of sigma square, and we are considering that the variance concept is 0, variance concept is constant with respect to time, and the parameter theta is with respect to the moving average, and that would be multiplied by the idea of the error, which is at 1 lag time period. Now, if the error does not have any variability change, then obviously solving those problems would be much easier for our case. But if the error term has, even though in our case we are for simplicity we are taking the error term with a constant variability, if the variability keeps changing, if you remember that we will have the second moment exploding and there the idea of non-stationarity would come into place without the concept of stationarity. Using back shift operator, I will come to that, we can write the following equation, which is phi into phi function of b into x t. X t is basically the time series, and that would basically mean the theta, which is corresponding to the moving average component, that function of the back shift operator b into the error, which is epsilon suffix t, and where small phi b and capital Phi b are the linear filters, and the properties are given accordingly based on the assumption. Now, the properties: a stationary solution of Arima 1 equation exists if and only if the corresponding concept of small phi is plus minus 1, then the unique stationary solution is given as required. And here the concept would be that x t would be casual function of the error, and x t can be represented in terms of the current and the past value depending on the error term which you have. And x t would be here this z t depending on the assumption you will take as the error, and you can basically formulate as. So, this if you remember this small phi is the corresponding Arima error weightages which you are giving, and that would be multiplied with the corresponding error term of z t minus j. Now, let me show you a simple this part, considering say for example, I am going to take the NSE data. So, NSE data which I will take, I will consider the closing price, and also to make things more interesting, I will take the concept of returns also. So, I will mark the returns field and save it. So, that means when the Excel files are shared, it will be easier for you. So, now I will mark there would be 3 type of returns. I will mark it as small r 1, then I mark it small r 2, then I mark it capital R, and what they are I will discuss. So, I will mark it with the color. So, that means all of us are aware what the headings are. Now, what is small r? So, if you understand from financial data, because this is a financial data, that is why we are trying to utilize the concept of time series. So, small r is basically the corresponding returns based on the concept of continuous compounding interest rate. Then R 2 would be the corresponding simple interest rate based on the difference of P 2 minus P 1 in the numerator divided by P 1, and capital R would be the total return again, which is a simple ratio of P 2 by P 1. So, because as this whole process will need some calculation. So, and considering this 54th lecture time is almost 30 minutes. So, I will stop here and continue the discussions for the time series, considering the closing price again I am mentioning, and I am purposely taking time series of financial data, R 1 return, R 2 return, and capital R. What are the formulas? I have mentioned them verbally. When I do the calculations, I will come back to that later on. Thank you very much, and have a nice day.